This video is capacitors. Capacitance is a measure of the charge storage or energy storage capacity of two conductors with an insulator in between when they gain equal opposite amounts of charge Q. When a capacitor is charged, the two conductors differ in electric potential by the amount V. The equation definition of capacitance is the charge divided by the potential. We're going to be seeing that equation quite a lot. Letter B, the equation relating the potential difference V, the electric field magnitude E, and the separation between the plates is right there. The potential difference between the two plates of a capacitor is numerically equal to the strength of the electric field times the separation between the plates, which you can see in the upper right corner there, is marked with a distance d. The unit for capacitance is the farad, named after Michael Faraday, symbolized by capital F. A farad is a pretty large amount of capacitance, so often capacitance is going to be in microfarads or nanofarads, but that's the basic variable. In the figure, assume that the capacitor is charged with a battery of voltage V, which moves charge from one plate to the other, resulting in the plates having equal and opposite charges, as well as creating a uniform electric field between the plates. In the figure, put the one-letter symbol with sign indicating a net charge on that plate. All right, let's do that first. The one-letter symbol that indicates a net charge, well, that's going to be Q. And this one will have Q as well. One of them will be positive, the other one will be negative. And a standard symbol that indicates that that charge is distributed over a given surface area. That would be the surface charge density. And again, we should put a sign in front of that. So this plate here has gained charge. The plate on the right has lost conventional charge. And there's a certain amount of charge per area. That's what sigma is. Also, sketch signs along the plates to show the distributed charge. So let's put a few signs here. However many positive signs we put on this plate, we need to put that same number of negative signs on that plate because the amounts of these two charges are equal to each other. They're opposite in sign. And then let's draw some electric field lines. Electric field lines run away from positive charges and towards negative charges. And since this field is uniform in here, I'm trying to draw these electric field lines equally spaced. That's pretty good. We're not going to show the fringing that would occur at the bottom and the top of this picture. All right, let's finish then by writing the equation that relates the symbols from part 2a to each other, and that was Q and sigma. And the surface charge density is coulombs per square meter, so Q divided by A. And now we want to derive the equation showing that capacitance C depends only on properties of the capacitor and fundamental constants. We said that the voltage between the plates, we said this on the previous page, was equal to the electric field strength multiplied by D. And we also said, what other equations do we have? We have the definition for capacitance, which is Q over V. Let's just start working this and see if we can find an equation for capacitance that shows that it depends only on the properties of the capacitor and fundamental constants. And that's not what this equation is showing, is it? This is showing that, oh, there's a certain amount of charge Q on the capacitor, and there's a certain potential between the plates, and that could differ from one case to another. So that equation is not showing that the capacitance depends only on the properties of the capacitor. When you don't know what to do, right, do something. How about we change this numerator into, let's take this top equation and say that Q is equal to sigma times A. All right, well, we're getting somewhere now. We have the plate area, which is a property of the capacitor. That's something. How about we change the denominator into E times D by that equation? This plate area, that is a property of the capacitor. This plate separation is a property of the capacitor. That's good so far. Now, what about sigma and the electric field? Those are not properties of the capacitor. That is how it's put together. I think somehow we need to get rid of those. Well, a long time ago, we went through an equation that said whenever you had charge distributed over a surface, the electric field strength in the vicinity of that surface was equal to the surface charge density divided by epsilon naught, which is the permittivity of free space. And so from that, I'm looking here and we can say, there's a sigma, there's an E. With a little bit of manipulation, we can result in that equation right there. So that's another equation that we could use for capacitance. That one shows clearly that the capacitance of a capacitor depends only on how it's put together and a fundamental constant. There is another variation of this that goes like that. Depending on what the insulator is between the plates, we call that a dielectric. It has a dielectric constant, and the equation then is just modified to show that. If there's air between the plates or a vacuum, then K is 1, and so that top equation, of course, applies for that case. But in general, that dielectric constant should be put in there. That's the equation that shows that the capacitance depends only on the construction of the capacitor.